Okay, this team develops a new way to generate powerful and focused X-rays using electron wave shaping.
Yeah. So again, more scientists out of Asia here, but university in Singapore, they've developed a new simulation-based technique for generating highly focused and powerful X-rays using a process called electron wave shaping. So through modeling how electrons interact when passed through a phase plate that modifies their wave pattern, they showed electrons could be sculpted to produce X-rays up to 1,000 times stronger than conventional methods, while also allowing tunable control over emission directions. So just a couple of things here. Electron wave shaping refers to a technique. What it does is it manipulates the wave properties of electrons in order to control and optimize the production of X-rays. So for those quick science thing, electrons have wave-like properties. And it's described by quantum mechanics, just like photons. But their wavelength can be changed through interactions with electric and magnetic fields. So in the context of this, with X-rays, electrons are accelerated and fired at a target material. As they collide and decelerate, X-rays are emitted via some effect. I can't remember what the name of it is. So conventionally, the electrons have an undefined wavefront, resulting in divergent, low-intensity X-ray emitted over a wide range. Electron wave shaping uses devices like faceplates that apply voltage gradients to controllably alter the electron's wave patterns as they pass through. So by shaping the waves, their probability of interaction with the target can be increased, which results in higher yield of X-rays, which gives you the higher resolution that you can expect with this new technique. So by precisely matching the shaped electron waves to interfere with atomic positions and we're talking graphene too, in a graphene target, they concentrated X-ray production. So adjusting the plate voltage, what it did was it transformed emissions to directionally focused beams. So potentially this promises tabletop devices using less energy than large X-ray tubes, enabling a lot of new applications potentially again.
So reading this, the big difference between the normal method and this wave shaping electron method is before you just shoot X-rays at it, and now we're focusing them in a intense in a specific direction. So they're more focused, they're intenser waves, but they're also like directed in one direction, so they penetrate better rather than scattering more.
Yeah.
So I'm because there's this thing called Bremsstrahlung, which is breaking radiation.
Yeah, that's the effect. That's the radiation. Yeah.
So or breaking radiation, which sounds like good. So what we're doing is we're making it so strong that this Bremsstrahlung radiation or breaking radiation happens less. Like it seems like a protective barrier, and we're ramming right through it. So does this mean there's less radiation scattered in the room, so people have to be less protected? Or does it, from if it's a person being affected, it seems like the effect of the radiation of the X-ray would be magnified on that person.
I don't think it's more of the intensity or magnification. It's more of the focused beam, if that makes sense. I don't know if there's more X-rays that are being produced, or if there's less. You would think though that if you're getting a more fixed beam, that there might be a more focused dosage of X-rays that are gonna happen. But based on this, from my understanding, and again, not an expert, but they need a lot of power in order to generate X-rays using traditional scanners. And so if you're able to reduce that power and focus that beam more, potentially you're going to get less X-rays produced, but in a more focused area, if that makes sense, as opposed to a more general area.
That makes sense.
I don't know.
And it says that you can now use this for finding defects in like electronic circuits or something. And I'm like, is that a real practical use?
So yes, actually, you know what? So this is more, we're getting into some spy kind of stuff. But this is how other companies will figure out the architecture of other manufacturers' chips by using X-ray technology. So that they can see how they can see the chip's architecture by just shooting X-rays at it. And they currently do this right now.
Yeah. And so, but why would we use it to detect flaws in semiconductor chips accurately? Are we?
So as we, so this is just me again spitballing, but as we get smaller and smaller on the nanoscale of wavelength to produce these chips, the defects, I'm guessing, are becoming smaller and smaller and smaller. And so having a higher resolution would probably help to find and identify those defects in those new chips that are being produced.
Yeah, so the chips coming off the line, we got three 3-nanometer chips being made now in processors.
So.
And
maybe even 2. I can't remember, but
I think there might be in we were talking about some new cool stuff, but the ones I think Apple are shipping now are 3 nanometers.
Mm-hmm.
And I'm just looking at this thing. Okay, so what we're doing is being able to detect what the yield rate is at closer to manufacturing and tweaking the results. So if we're getting a 50% failure rate, we can scan these right when they're coming off to detect where they are and fix the manufacturing process, kind of thing.
I'm thinking yes, absolutely, yeah.
Cool.
Yeah. You know that and correct me if I'm wrong. I think there's actually only one company, and I think they're based out of Norway, that produces the machines to produce chips. TSMC is one. I can't remember, but don't hold me to this. So if I'm wrong, let me know, guys. But I think there's one. There might be 2 that produce the actual machines, that manufacture the machines to produce chips.
Yeah, this is and Sam Altman, isn't he trying to raise $7 trillion to build his AI fab company to build chips?
Is he? That's
Yeah.
a lot. Did you know, speaking of quickly AI, there is a Canadian company that has developed a phenomenal chip as well as new encoding or a new technique for AI. It's called Grok, GROQ. Anyways, we diverse, but yeah.
If you know these people, let's see if we can get them on and talking about their product.
Yeah.
Back to this. So I can see, they're talking about probably using that example to talk about the level of resolution they could get to potentially.
Yeah.
When I'm an old man, I've been married, I have kids. My wife was pregnant in the US, and we did the first ultrasounds down there. And what we got down there was much better resolution than what we received up here. And US versus Canada, when I say down there, up here.
Yeah.
This probably takes those things to a whole new level. And being able to use these in all sorts of industries to do exactly that. If we go back to talking about liquid metal printing and those DNA nanorobots, and we could be pumping these off the press and having tools like this detecting the defects early on, because I don't doubt they'll be 100% perfect.
Yeah, well, in order for us to get this technology and do it, Canada needs to invest a lot more money into research and development. But there's a lot of potentials here for for this technology as well too. So it's really, I think we're about 5-10 years off from practical tabletop devices for this. But
yeah, and when we say practical tabletop devices, what does that mean?
well, where it's commercially available. So
But you go to the doctors and they're using something that's not going to be anywhere near this, and everyone, you got to wear this big leaded thing. You got to stand behind the wall. So you just pick one up and shove it on your desk at the office. People want to come in and scan stuff. They come into Bob's office and press the button.
No, I think we're talking like GE, where they're selling to these devices to hospitals and things like that. I think that's where we're at. And we do have, I know we have portable X-ray machines now that can fit inside of a truck. But yeah, I think in a clinical setting, we're talking 5-10 years away.
Yeah, this is really cool, and I'm only scratching the surface of what we could do with this technology. I'm very curious, and so always have to go to the dystopian Craig. And I got a couple other questions probably for you here. I just wanted to talk about my dystopian. Does this sounds like we could make beam weapons out of this technology?
Absolutely, we could. Actually, to be honest, maybe it all depends on how far the electron beam, how much of it dissipates over a distance. So depending on the beam itself, and the power behind the beam, who knows how far you can actually, shoot that beam, if that makes sense.
They didn't really talk about, I didn't see here whether it takes up more or less energy doing this or the same.
I think it takes up less energy, because you're more directed as opposed to, so typical X-ray tubes require kilowatts of power, whereas what I'm assuming is this tabletop, if you're using wave shaping devices, they can function with watts instead of kilowatts.
What other areas of physics research could benefit from this electron wave patterns other than X-rays?
Well, yeah, we talked about the chip industry. There's photonics, so imprinting quantum states onto shaped electron waves. That could open up interacting with light and matter in new regimes. And I know we talked about light and time and different things like that. So that one's really cool. There may also be opportunities to coherently control, like using the techniques here, they could, beyond just X-ray generation, they can control other emitted radiations through tailored electron material interactions. There's different things like tunable oriented light beams. It's a lot of really more complex physics and areas of physics that this is more, but electron diffraction. So if you could control electron waves, you could tune diffraction patterns for structural characterization with even greater sensitivity. Like, there's a lot of stuff. So essentially, where electron beams are used to probe or excite matter precisely sculpting, it could unlock new capabilities in the quantum kind of realm, if that makes sense.
I think this could be used in all sorts of ways, and we're just scratching the surface. So I'm really interested in electron wave shaping. I think there's limited uses to the X-ray part of it, but I think this is going to change a lot of different scientific fields.
Yeah, I think one, if we're talking about from the medical perspective, mammography could actually benefit.
Absolutely.
Well, yeah.
Yeah, I could see all sorts of from that. Yeah, absolutely. Then that's a huge problem. So
for sure.
This is great. You have anything else you want to add to this before we jump to our next one?
No, just like there obviously are safety concerns, because and you were talking about the radiation dose. So even with the ability to focus X-rays, there's always unintended exposure that could lead to excessive radiation absorption in tissues. So obviously there would still be like strict emission control and shielding that would be needed. But again, there's still, so if those of you out there thinking, oh, we won't need to use those lead vests or any protection, we're still going to need that. It just might not be as predominant, but there's going to be new techniques that are going to be needed for this. So
definitely, I'm really interested. Like I said, whenever we get to this level, it's really cool. I used to work, do IT work. I was an outsourced IT guy for a company called Gleg Water, and I handled all their systems. And one of the coolest things they did was they made water that was either so acidy or so alkaline, so pure that Intel and whatnot used it in their chip building process to get rid of any impurities and all this kind of stuff. It's really interesting, this whole process at this level.